Or I think it's some keys to success in calculus. RUFF, rough. Doesn't have to be. And then end with a related rate problem that it's just be kind of cool to be able to do. It's pictured here, the start of it. So my keys are this. First, read. Reading is the best preparation for anything. If you can read, then you can learn it. It doesn't just apply to calculus, but so much of calculus, I find, having taught it for over 50 years, is that one of the challenges is just being able to read what a problem is telling you. The tools of calculus, particularly nowadays with modern technology, can be mastered, but to use it, to apply it, it helps if you can read. And then my second key was use, and that's to use what you have read. Really. If you use it, you often remember it. It's not the old saying says calculus is not a spectator sport, but you got to be able to read, but then use what you've read. You tend to remember things more, honestly, if you read it and kind of learn it yourself than if somebody speaks it at you. I may be speaking at you a little bit in this video, but you retain it more if you read it yourself. But it needs to be fun. That's my third key, fun. Calculus, just like so many things in life, to be good at it, you kind of have to like it. You gotta let it be fun. You can find success by reading and then just having a fun go at it. Relax while you're doing it. Have a drink, any kind of drink. It's only calculus, and it really is fun stuff. And then my fourth key is to fantasize. And really, again, daydream about success in calculus. See yourself mastering related rates, for example. That's one kind of calculus problem. Watch another of my videos, and I'll actually show you how to imagine a related rate problem that could lead to destroying the world, if you ignore the physics involved. But I'm not kidding about daydreaming. You can lie down, stand up, just think about what you read, and just try to imagine doing it. It's amazing how much you can imagine doing if you try. I mean, just really the key is to you might almost call this a RAFA, an A on the end. Attempt, make an effort at it. The picture here you're looking at is myself in the foreground, still tucked. It was 12 years ago, with my brother, best friend, at the Camp Challenge in Sorrento, Florida, a little camp for people with some physical challenges. We were counselors there. It's a 50th year reunion. That was 12 years ago. So the picture's 12 years old. Actually, here I am in mid 60s at Camp Challenge. You can ask me there, lifting one of my campers onto the Sorrento Fire Department fire truck. They always back then came out and let us play on the truck. Well, back to fantasizing and math. So I am dreaming about a car driving down the road. I see a balloon rising. The car is beneath the balloon. The car keeps going. The balloon keeps rising. So there's an animation of the calculus problem we're going to look at. This is a problem that is pretty challenging, and I would venture to say if you ask 1,000 people in the world if they could figure this out, that you'd be lucky to find one that said he or she could. So I'm saying that if you master this problem, you're among the elite people in the whole world. Just to be watching my video means you must be among the elite people in the whole world, because it means you care something about calculus, which is wonderful. What calculus can do is extraordinary. Car is going 40 feet per second. The balloon was 10 feet high when the tail of the car passed under it. The balloon is going up at 20 feet per second. So the balloon was 10 feet up in the air. The car slipped under it. It was 10 feet up in the air when the car had just about cleared it. Balloon directly over the back end of the car, 10 feet above the ground, let's say, going 20 feet per second. So there's the balloon going up. The car has left, and I'm dreaming about a theorem in geometry here called the Pythagorean Theorem. We got a right triangle, keeps getting bigger and bigger and bigger here, and the balloon's going up at 20 feet per second. Car is traveling at a right angle to the path of the balloon at 40 feet per second. What I want to try to figure out is the hypotenuse of this right triangle, that line segment there going from the balloon down to just under the car, which I'm saying is going to represent the distance between the balloon and the car. How fast is that increasing? And we're going to be increasing at a constant rate. If the balloon is going up at a constant speed of 20 feet per second, car traveling at a constant speed of 40 feet per second, will the distance between them be changing at a constant rate or not? And if you can figure that out, you're among the elite people in the world. Is my thesis here. Well, I know we're all wondering the same thing, aren't we? Will the balloon pop in the animation? Maybe it should have. Maybe it will. No, not this time. I'm wondering how fast the distance between the balloon and the car is changing. Like 1 second after the balloon is directly over the rear of the car. And is the distance between them always changing at the same rate? So there they are. Seeing it over and over again. Can I see how to do it? Well, I'm not going to read this to you, but this is the challenge, I say, one of the challenges in calculus. To solve a problem like this, you have to be able to read what's on the screen and make sense of it. And what a lot of people do is they'll read it once and say, I don't get it. Read it a second time, didn't get it any better. Read it a third time and say, oh, I can't do this. I can't do a word problem. Just can't. But that's not the way you try to do a word problem. What you want to do when you read it is just pick out what it's saying little bit by little bit. Don't try to solve the problem at the beginning. Just figure out what the problem's giving you, what kind of info it's giving you, and then take it from there. So, for example, first step, just pick some letters. I wasn't very creative. I used X, Y, and Z. You don't have to use those letters. But pick them and let them stand for the distances discussed in the words you read. So I let X stand for the horizontal distance from the balloon to the car. Part of the problem, what's going on, is this horizontal distance from from directly under the balloon, horizontal to the car, and call that X. Not X sub 1, that's a hash mark. Let Y stand for the height of the balloon. So the distance from the balloon, bottom of the balloon, down to the ground in the picture here, called y. And then I call z the distance from the balloon to the car. So you can see z labeled in my picture, distance from the balloon down here, this point on the ground directly below the back of the car. Calling that the distance from the balloon to the car. Kind of idealized a little bit, isn't it? Now, once you have sort of written down the variables involved in the problem, giving them a name, the second step is to try to figure out an equation that relates the variables to each other. In related rate problems, you want to relate the variables to each other. Think Pythagorean Theorem. That was my dream of the problem. I was looking at it in Pythagorean Theorem. I bet Pythagorean Theorem is going to be involved. It often is in related rate problems. Pythagorean Theorem says that the square of the length of the hypotenuse of the right triangle equals the sum of the squares of the length of the two legs of the right triangle. We're assuming here the balloon's not being blown about by the wind, just going straight up, car going straight out, got a right angle in here at the origin of this little coordinate system I've introduced. And so Pythagorean Theorem can be applied, and so z squared equals x squared plus y squared. Then the third step is to try to sort out the rest of the information in the problem. Not trying to solve it, not just keep reading it over and over again, but try to just information in the problem. Like you got a red balloon rising at the rate of 20 feet per second. Now in calculus, there's something called a derivative, which one of its interpretations is to give an instantaneous rate of change. Here it's a perpetual constant rate of change. Well, the derivative of whatever distance is changing based on this balloon rate of change with respect to time, it's your 20 feet of distance with respect to time per second, that's represented by a calculus derivative. So if y is the actual distance changing when the balloon is rising, then this piece of information here, this rate of 20 feet per second, that's the derivative of y with respect to time, t for time, 20 feet per second. Balloon is 10 feet above the ground at the point in time when the back end of the green car is directly below the bottom of the balloon. Now that 20 feet above the ground is kind of important because it tells you that the distance y is a function of time. It's raising at 20 feet per second, so that'd be like 20 times time. Almost tell you how high the balloon is, but start out 10 feet above the ground, so it'd be 20 times time plus 10 would be how high the balloon is. It's a function of time. Problem says this car, green, is traveling at 40 feet per second. So something's changing at the rate of 40 feet per second. And that'd be this distance x. Car is traveling over at 40 feet per second. So in calculus, the translation into calculus would be dx dt equals 40 feet per second. And then when you're reading the problem, don't try to figure it all out all at once, but look for what you're trying to figure out. I put that in black. What is the rate of change of the distance between the bottom of the balloon, point on the ground below the car? Z here in labeling. So the rate at which z is changing is a calculus derivative. It'd be dz dt. That's what we're trying to figure out. So write down what you're given and what you're trying to figure out before you try to solve the problem. The key then is somebody letting you know a related rate problem in calculus, what you're going to have to do is differentiate implicitly. Means you're going to differentiate the whole equation, here it's written down here, that relates the variables with respect to something. Usually not one of the variables, but usually, quite often, time. These x, y, and z are all functions of time. You can differentiate them with respect to time. They're being assumed to be differentiable functions. And the relationship between them, based on Pythagorean theorem, can be differentiated what's called implicitly with respect to time. If you're differentiating with respect to something other than one of the variables, for sure, you'll be doing what's called implicit differentiation. So you're going to differentiate that with respect to time. So you kind of need to know how to do that, don't you? Alright, so dx dt is 40, dy dt is 20, trying to find dz dt, and I asked to find it after 1 second from whom they were like that. Starting out, they call that time zero. Might as well make it as simple as you can. And then 1 second after they're in this spot, so no, traveling, and I'm going to try to stop it at about a little past here, but that's the idea here. We're going to try to figure out that after 1 second, x would actually be 40. Point underneath the car will be right here at 40 after 1 second. It's traveling 40 feet per second, so after 1 second, x would be 40 feet. Balloon was already 10 feet above the ground. I know that at t equal to 0. So at t equal to 1, the balloon is going to be 30 feet above the ground. Y will be 30. S squared plus y squared equals z squared. Figured that out before. Not trying to solve the problem. You're just trying to figure out what all we know. So at 1 second, at t equal to 1, z would be the square root of 40 squared plus 30 squared. Not a 20 here, but a 30, remember. Y is 30 at t equal to 1. And that computes to 50. So at t equal to 1, z is 50 feet. So distance between them is actually 50 feet after 1 second. Now, to do implicit differentiation, you're using in calculus something called the chain rule. Chain rules say if you differentiate, say with respect to t, a composite function, say x of t is some x of function of t, and then that quantity squared. With the squared function, apply it to the x of t function. This isn't x times t, it's x emphasizing as a function of t. Chain rule says you differentiate that, you differentiate the x squared with respect to x, you get 2x as a function of t. And multiply that times your derivative of what's called the inner function, the x of t in here. Then it's being squared, so that's just x prime of t. Chain rule, which is just 2x times dx dt. I'm going to have to write down the emphasis to x is a function of t. Same idea for the other two. So if we differentiate this equation 1 with respect to t, for the x squared part, we get 2x times dx dt. For the y squared part, 2y times dy dt. For the z squared part, 2z times dz dt. Cool calculus. Now, if we substitute in the given information, what that produces is your dx dt, knew that was 40. Dy dt, knew that was 20. dz dt is what we're trying to figure out. See, I ain't trying to figure the whole thing out all at once. You just got to do it in steps. This is my last step here now. Because now it becomes an algebra problem. You just got to solve this equation for dz dt. So we divide each side by 2z. I wrote the dz dt on the left. On the other side, we got multiply that out, you get 80x. Multiply that out, get plus 40y. Then divide it by 2z. You're reducing, divide numerator and denominator by 2. And the rate of change, the distance between the balloon and the car with respect to time, is 40x plus 20y divided by z. So at any point in time, compute the x, y, and z values at that point in time. You can compute how the rate of change of distance between the car and the balloon. So dz dt, when t equals 1, putting in the results of t equal to 1, meaning x would be 40, y would be 20 plus 10, 30, z would be 50, we get that, do some arithmetic, 44 feet per second. That's the rate of change of the distance between the balloon and the car after 1 second. Here's the animation again. At t equal to 2 seconds, x would be 80, y would be 50, z would be a little more complicated, but it would be in simplified graphical form, 10 times the square root of 89. So you put that input into this relationship here, and it turns out the rate of change, the distance between the balloon and the car, after 2 seconds, is slightly more, 44.52 feet per second. Exactly this number here. So in fact, that distance, this distance here, isn't changing at a constant rate. And in fact, at 2 seconds, changing a little faster than at 1 second. Now that's a pretty tough problem. I'm not going to deny it, but step by step, it can be done. Didn't really have to know a lot except for calculus, how to implicitly differentiate the chain rule. I really do believe that probably only 1 out of 1,000 people could do it. So if you were able to follow what I just did, you're among the elite people of the world. Cool to be that. And kind of fun to be that. Still a little bit dangerous out there, so hope everybody stays safe.